All right, pause, read the question. Go ahead and draw the picture on your own. Try to do this on your own before watching me do it. Okay, I hope you did that. We've got ourselves here a cone. And we know when it's completely full that the radius up here on the top is 1 foot and that the total height is 2 feet. And I'm told that the volume is changing at some rate. So dV dt, the rate of change of volume. Now water's draining out. So see, I've got some water in here. That's going down. So my volume is decreasing at this rate. That means that's a negative derivative. My dV dt is negative 0.03 cubic feet per second. That's how quickly I'm losing volume. I want the change in height. So that's my, maybe we'll call this R0, H0. That's the maximum radius, maximum height. I've got some height and some radius that are both functions of time here. As this thing goes down, the height's going down. And as the height goes down, I get smaller and smaller cross-sectional circles. I want to know how quickly the height is changing, dH dt, when at a particular moment in time, when h equals 1/2 foot. So I need some equation that relates all of my variables. I've got V, R, and H are all functions of time. So that's your main goal. Like once you get that, related rate problems are not too bad. Find some formula that relates volume to radius and height of a cone. And that's just volume of a cone in this case. And you might have to look that up. That's 1/3 pi r squared h. Okay, now I'm going to show you a shortcut on this problem. Like when I first started writing up my solution here, I started doing this the long way, and you can get there. But this works, what I'm going to show you here works on any kind of cone problem. This triangle I get right here is a similar triangle to this one. So I'm going to draw these triangles out. So this is the full thing. When this is 1 and this is 2, that's this triangle here. That's a similar triangle to this guy here, where this is R and this is H. So there's a relationship between R and H in a cone. This works for any kind of cone problem. Later on, when we're doing Riemann sums, when we're doing some advanced calculus 2 problems, when you're doing hydrostatic pressure, there are a lot of applications where you can draw this similar triangle here and eliminate one of the variables. And that's going to make this problem a little easier. So let's use our similar triangles here and say, let's see, H relates to 2 in the same way that R relates to 1. In other words, R is H over 2. That means I can write volume as just a function of H. Otherwise, if I didn't do this, when I start taking the derivative of both sides, I've got a product here. I would have to use product rule. And then at some point, I'm going to pick up a dr dt. I would have to figure out how quickly the radius is changing, because that's not given. They only tell me dv dt. I would have to do a little more work to figure out, well, if H is changing at this rate, then how quickly is R changing? And we could get that from here. It's the RDT, just take the derivative of both sides, would be 1/2 dH dt. And so I could do product rule on this. Let me write it out so you can see what I'm saying. Take the derivative of both sides. I'm going to erase all this in a minute. 1/3 pi comes along for the ride. And I have to do product rule. Derivative of the first, 2r times dr dt. R is a function of time. I have to use implicit differentiation. Times h. Plus, leave this first one alone. Derivative of h is dh dt. That's who I want. That's what I'm after. And I want that at a particular moment in time. So I could plug in my h right there. I now need to find r. I would need to go back here and find r when h equals 1/2. So r would equal 1/4. Plug that in there and in there. dr dt is 1/2 of dh dt. So that would be like, I would have to add like terms there. dv dt I was given. See, there's a lot of arithmetic in here, but it can be done. I'm going to go back a little bit and show you a shortcut instead. I know r as a function of t. Here, I can erase this. I don't need this. I know r is a function of h. Sorry, right there. So let's just plug that in right there. V then is 1/3 pi h over 2 squared. And I've got this other h that's coming along for the ride. So I'm going to get an h squared times an h. That's an h cubed. The pi comes along. And then I'm going to get 2 squared is 4 times 3 over 12. So now I have volume written just as a function of h. Keeping in mind that both of those really depend on time. Then dv dt, taking the derivative of both sides with respect to time. The pi over 12 comes along for the ride. Derivative of junk cubed is 3 times junk squared times the derivative of the inside. The derivative of h with respect to time, we write dh dt. That's who I want. That's what I'm after right there. That was my goal. I know that is 1/2 at the moment I care about, and this one's a constant. This is an equal sign right here. That was negative 0.03. So we get negative 0.03 equals pi over 12 times 3 times 1/2 squared dh dt. That's a times right there. Okay, so you can check all the arithmetic here. You would find this divided over. What we're going to get is dh dt is negative 0.153 feet per second. Definitely check the arithmetic there so that you believe it. Why is it negative? Because h is going down. We're losing water. Right? The height of this water is draining out here. Height's going down. So the derivative should be negative. Why do we have these units? Because height was measured in feet, time is measured in seconds, dh dt. For units, think of the derivative as a fraction. It's always going to have units of this guy per units of this guy. Derivatives always have units of fractions, top over bottom. In this case, feet per second. It's a good place to stop.